Emmanuel, or we can go ahead and can introduce you now if you're ready.
Yeah.
Okay, well, welcome everyone to the second day of the Learning and Testing in High Dimensions workshop. We're very lucky to have Emmanuel Abbe today, who will tell us about learning and testing for gradient descent.
Okay, thank you very much, and thank you for the invitation to talk in this workshop. So I think I tried to adapt to the theme of the workshop, and essentially what I'll tell you is instances where we use testing to get lower bounds for gradient descent on the neural networks. I'll first tell you about how to get those lower bounds for general networks, and I'll define these. And then I'll give you an application in one special case for how spectral algorithm and GD compare on some graph testing problem. So first I'll define what I mean by GD, SGD, etc. So GD, SGD with parameter n here refers to the mini batch size. So the setting is you get your net initialization W0. I'll discuss next how this is, what kind of initialization is allowed. You have your loss function, your sequence of weights, and then you iterate the usual recursion of SGD. You update the weight with here the gradient loss, and the setting is that you get m fresh sample at each time step. Okay, there are IID from this distribution Px, and this notation P hat SM is the empirical distribution of these m fresh samples. So this is this expectation is exactly being the empirical average of this fresh batch. Okay, so you iterate this up to capital T time, and you produce a function which shall denote typically f at of W at time capital T. All right, so that's for the SGD. Now, for the type of neural networks that we allow, I guess the approach we're taking is rather than trying to model what's allowed or not in terms of architecture, is it ID fully connected? Is it this, which is not necessarily the most relevant? Is it CNN or something more fancy? Is it a combination of these? We will essentially go to the extreme and just assume that we have what I call poly networks. So this is simply any kind of architecture that we want. So it has to have polynomial size. Okay, so the number of edges must be polynomial in the input dimension. So everything that I'm talking about is going to be polynomial in the input dimension n, which is the dimension of the axes that we feed to the network. And for the positive part, it's going to be just the new network is going to be some directly dissected graph with some linearity. For the negative results, it can be in fact any differentiable model. And then for the initialization, it can be a general, but it has to be a valid initialization, which means you have to come up with initialization in poly time. You can't cheat and do something crazy. But of course, it has to be not dependent on the data for training and testing, and also it has to be agnostic to the target function, although it may use some prior hypothesis class or some realizability assumption I'll discuss. So what are the learning requirements? So I'm going to work in the Boolean setting. So the data is just binary vectors of dimension n. The labels, there's two classes, plus minus one. Px, as I said earlier, is the total distribution in the inputs. And then we'll have a subset of functions, the hypothesis class, or sometimes we will work with a total distribution on function. And what we will ask in either cases is that we have balanced classes. So the two labels, plus one and minus one, are essentially appearing with slowly half for the marginal. Okay. And now the learning requirement, well, when we work with the setting where we are given a fair distribution for the input and for the function, for the target function, we'll say that an algorithm has an edge of alpha. So an algorithm is something that produces an F ads, and this depends on, of course, the samples and whatever randomness the algorithm may use. And so the obtaining an edge of alpha means that your algorithm produces a label on a new fresh sample X that is incorrect compared to the true label with a probability which should be inequality, less than half minus alpha by 2. Okay, so that's the requirement. And this is the learning for a pair distribution because I'm taking my probability here. Of course, probability over the samples that you use for training, but also averaging over the x that is the new fresh sample, and also averaging over the function f drawn from my class. Okay, so that's a typical learning version, essentially, average case learning version. And of course, okay, let me first define the other one. The other one is the more classic one, where you have learning for a class f of the function, and you get learning with an edge alpha. If this time I'm going to put the worst case over the functions in the class and over the distribution on x, in the same requirement. And of course, if you fail at learning in the first condition here, then you also fail at learning in the second condition. So if for some choice of px and pf you fail, then for some alpha, then you also fail for the second requirement. Now the choice of alpha depends. The weakest one is when you only get a polynomial edge, so something that is not exponentially small, in which case it better be that at the beginning here, this was already something which is for sublinear. And you can have a constant edge, which like a weak learning, and you can have an edge which gets as close as you want to 1, and that will be strong learning or pack, and I put a bar on the pack here, because normally in pack you have the epsilon delta event, but here I'm joining them by putting a single probability event. Okay, but this is essentially this is equivalent to that. Okay, so the last slide of definitions, it's a bit heavy, but then we should be set. Let's first define what I call poly SGD and N. So this is the class of function for which there exists an initialization of the net, which depends only on the class of function. And it has to be polytime, so in particular, the net has to be polysized. And there is a loss function, such that if you run SGD with all parameter polynomials, so that's the number of times that has to be polynomial, and there's this SNR here that I will explain in a second. Then you achieve, and this is the same requirement I have on the previous slide, you achieve this edge of alpha in the worst case. Now I'm going to define the exact same thing for GD instead of SGD, except that now I'm adding this supremum over all the n more than 1, where remember that n is the batch size. In other words, I'm forcing for the class poly GD, I'm forcing to succeed with n that could be as large as you want, in particular infinity. Okay. And then the third class is going to be poly SQ. That's the class of function for which there exists an SQ algorithm that uses poly many queries of poly SNR, such that again you produce the same requirement as before. And now let me tell you what this SNR that shows up in all these three things. So when you look at the queries that you make in GD, so if you call this the function GP, what you do when you run SGD is you take an expectation of some function GT that depends on X and the target function F. And what you have here is this empirical distribution P at over the sample. Now, if you do statistical queries, what you would have instead here is an expectation which is over the entire population distribution. So it would be expectation of X over Dx of some Qt function. And you have plus minus some precision sigma that is due to the fact that you don't want to work in a setting where the queries can have arbitrary magnitude and the noise can be arbitrarily small. So what I call the SNR is precisely the ratio between the magnitude that your queries can take. So there will be plus minus C. So C is the range of Qt divided by sigma. This is going to be the SNR of your queries. I don't want to derive results that are going to exploit infinite precision or things like that. So that's well defined in SQ, and in fact, typically in SQ, C is equal to 1. So 1 over sigma is the SNR. And here we'll add up the same for SGD or GD. We'll ask that the ratio between the range of the gradient of the loss and the noise that you add has to be polynomial. So you don't want to work with infinite precision when you run your SGD and infinite magnitude. So that's what this SNR refers to. That shows up in all these contribute here. You work with polynomial parameters also for the ratio of magnitude per precision noise. Again, the last class is the polyalg, and this is the class where you don't have any constraint. It's just there exists an algorithm that runs in polytime that uses poly many samples such that you achieve your edge alpha. Okay, So this is the forecast. You would expect that the last one is the most generic one, that SQ is the next, and then between those two, naively perhaps GD with larger batch shouldn't hurt, but the results are perhaps slightly surprising, and they are as follows. So first of all, there is a equivalence between the class SGD, poly-SGD, and polyalg. So you have that. So you have that for any alpha that you fix between 0 and 1, then whatever you can do in polytime with some algorithm, you can also do by running SGD on such a poly. So that's this university result of SGD. And then you have the separation between poly-SGD and both poly-SQ or poly-GD. And the separation is so the values that I have in here say that here you can have the strongest requirement and here the weakest. So there are functions that you can learn with arbitrary, with an edge which is arbitrary close to 1, with SGD that you cannot even learn with polynomial edge with either SQ or GD. And these are the functions that I will discuss in a second. And also we know that these two are in fact the same, poly-GD and poly-SQ. So really the separation is between those two words, the GD and SQ, and the SGD in the effective algorithm. Okay, so any questions on this? I'll then start to talk about.
Can you explain again why is so SGD is not SQ? That's what you're saying here.
Yeah, there's a separation. There's a separation between SGD and SQ. So they are
just like a super intuitively, why is that this separation?
It's because SGD, you're not forced to take averages over the entire batches or very large batches. You can take a single sample at a time. So it will allow you, when you are in this framework of poly networks for initialization, it will allow you to run algorithm like Gaussian elimination, which you can do with GD or SQ.
I see. So it's a single sample power that that gives you the edge. Okay.
Exactly. Yeah. Right. Okay. So now I want to tell you a bit where testing comes in. It's for the lower bound. So the lower bound looks like this. The probability that you get the wrong label with your algorithm output at time t. This is remember that's what you get when you run with SGDM for 3-time step. And you don't get the right label with a probability which is lower bounded by half, which is because the classes are balanced. This is the trivial value minus this ratio of these two terms. The GF is the jump flow and CP is the cross predictability, and they are defined like this. So the jump flow is going to be the power series of the expected gradient norm when you go through your time steps, divided by 1 over sigma, which remember is the noise precision, the noise variance of standard deviation. And then let me first cover both, and then I'll get back to the jump flow. And the cross predictability is some sort of average notion of statistical dimension. It's the correlation you get between two functions that are sampled from your class. When you take for the measure in the correlation, you take the empirical distribution of your mini batch. Okay, so let's look at the jump flow first. If you want to upper bound this crudely, what you can do is simply say, okay, there's the 1 over sigma that is here. I'm going to upper bound this by t for the number of time steps, and then I'm just going to upper bound each summon here by the number of the dimension of these vectors. So this is the gradient, so it has dimension the number of edges in the graph in your neural nets. And then the magnitude that each component can have, which is bounded by C. And C could be n to the 100. It's just the fact that you don't have infinite magnitude in your gradient queries. And so this thing will be poly n when you work in this poly SGD setting where all parameters must be polynomial. Okay, so clearly the jump flow is polynomial in n. And now if you look at the cross spread, if you write how this cross spread is expressed in terms of the parameter n, which is the size of the batch, so it gives like 1 over n plus, you can ignore this, it's equal to 1, or some constant, plus the Cp infinity, which is just the same notion, but when you take the population distribution for computing your correlation between two typical functions in your class. Now, this quantity here can be small. It can definitely be growing faster than any polynomial. That's, for example, the case if you take k parities where k is growing with n. So clearly, because the jump flow must be polynomial at most, and because the cross spread infinity can be super polynomial, if you take your n here, which is a large enough polynomial, then this quantity will smash down the jump flow and this tends to half. Okay, so that's the reasoning why large n will hurt you in some cases where this Cp infinity is going to be very small. But if you don't do large n, if you stick with n is equal to 1, like in SGD, then this term here is going to stick to 1. And so the cross spread cannot be small. And then this bound becomes loose and doesn't tend to halve. And in fact, then the second result here is going to tell you that there's a reason for this, is because with SGD, you can emulate any algorithm as opposed to with GD. Okay, so where is the testing coming? It's coming in the following way. When you try to show that the output of GD is not going to succeed, the strategy is that you compare how does GD behave when you train on true data. So W subscript F represents the algorithm, so the weights that are obtained by GD when you train with the right labels here, with the right data labels. And then W subscript star is going to reference to the evolution of GD or SGD when you train with the random labels here. So that means you don't get you get junk radical half labels. And the strategy is to show that the total variation distance between the distribution of the weights is going to be vanishing if t is not too large. So in other words, you cannot distinguish the algorithm output on the true or on the junk data. And therefore, by the total variation bound, the probability that you get the right label with a true guy here, or that you get the right label with a junk guy here, must be upper bounded by the TV. This guy here must be half because it's just independent of the true f, so you cannot hope to predict with junk data better than half. And if this guy is vanishing when t is not too large, then you get your lower bound. Let's say that you cannot generalize better than half. Okay, so now from there it becomes information theoretic inequalities, and that's why I like this approach, because now you just have to bound the TV, so this quantity here, and here I think the basic rules that I use is that for the TV you can write it as so the way I use the formula I use for here is just to put the definition that this is the supremum of the measure of the two measures for any events, or you can think of it as the L1 norm of the distribution, which allows you to use the triangular inequality in the TV, or you can think about it as the best error when you try to when you try to do hypothesis testing between the two measures. And in particular, this implies that there is a data processing inequality of the TV, which is that if you look at the TV between two unknown variables, it's always greater than the TV between a function and the same variable. Okay, so this is what you use, triangular inequality using this definition, and the data processing inequality allows you to show that you have this subadditivity of TV over the time steps when you run gradient descent, which is an important property. And then to bound each of these terms here, what you do is you typically upper bound the TV, so you can either do it by upper bounding with the KL, which is the thin-square inequality. And then the KL itself is going to be upper bounded by the chi-square, distance between the measures. And typically when you want to bound the KL, the total variation distance, it's convenient to go to the KL divergence, because you can have chain rules. But eventually, if you want to express those terms, if you want to show something tends to 0, you always end up by proving that the chi-square goes to 0, because the chi-square is in fact, this becomes tight inequalities when those measures become close to each other. So when you want to prove that the TV goes to 0, you end up with a chi-square term that is going to have some quadratic factors, and then you can typically do Cauchy-Schwarz, and this is how you end up with things that have quadratic terms of this form, and the Cauchy-Schwarz is what ends up with having two terms like that that separate. So obviously, I only wanted to cover the rough ideas without giving the details, but essentially this is the flavor of how you end up with a bound that looks like this by manipulating this information measure. Okay, so now for the last 10 minutes, I'll tell you about some application of lower bound when you don't have a Pauli initialization, but a random initialization of your neural nets. And here is the example. So it's back to the good old stochastic block model. You want to distinguish, so you want to decide whether you have two classes for your data. It's the data is either an adversary random graph of parameter NR, or it's going to be an SVM with parameter PQ. So that means you patch two adversary models on any of the two vertices, and you connect them with probability Q across the group and P inside. And we're going to choose that R is the average of P plus Q by 2, so that these two graphs have the same edge density. Okay, so the goal is going that I will select one of these two graphs, which probably half from class 1 to class 2, and you have to decide where it came from with a probability of error that is better than half. So you want to get half minus half omega of 1. So the edge has to be omega of 1. Okay? So that's the goal, and so that's the deep learning requirements. And because the TV, as we just said before, is half minus half the probability of error of the optimal test between the two measures, then what we want in order to be able to succeed in guessing where the graph comes from is probably better than half is that the total version distance has to be bounded away from 0 between the two measures of the two random graph models. Okay, so this has been studied now for some time, and we know that you can succeed in doing this even in the sparse regime when P is equal to A by N and Q is equal to B by N. And as long as the A minus B divided by 2 square is more than the A plus B divided by 2, which is the KS threshold, then this total version distance is going to be bounded away from 0. So you can solve this testing problem. Any questions on the setting? Soon I will also tell you how you could try to solve this problem with gradient descent when you see samples from each class, but for now it's the one-shot problem. Okay, so we have 2 more slides. Now, how do you solve this? So this was a total version bound gets positive in this regime, but how do you solve this with some test, with some algorithm? So one thing you can do is simply count cycles, just the moments. And what you have is that in the adversary model, when D is my average degree here, so D is going to be R times N, and it's remember that it has to be the A plus B by 2, because we have this balance equation here. If you're in the adversary case, this is the number of n cycles. So if you count the number of n cycles, then it's going to be equal to this in the adversary model. It grows exponentially with v divided by 2n lengths of the cycles, and this is the variance situation around that's the mean. If you count the number of n cycles in the SVM, then what you get is the same dominant term, the same fluctuation, but now you have this term here, which is due to the community presence in the graph. So as we can see, if this quantity m minus b by 2 is more than the quantity that I have here, which is a plus b by 2 square root, then in fact this is going to dominate the fluctuation that I have here, and therefore I can distinguish these two quantities. So you just need to take m that grows slowly, like for example log n, and then you will be able to distinguish between the two models by counting m cycles. Okay. Another way to approach this problem is through spectral algorithm. If you look at the matrix, the adjacency matrix A of the graph, let's look first at the expectation of A. Then what you have here is an eigenvalue of 0 of eigenvalue n of multiplicity n minus 1, and then an eigenvalue of d of multiplicity 1. In expectation, the block model, you have the eigenvalue 0 with multiplicity n minus 2, because it's a rank 2 matrix now. Still the d for the peripheral as before. And then here you have the a minus b by 2, which is the eigenvalue of the communities corresponding to +1 and this guy and -1 on the second community. Okay, that's in expectation. If now you go to the true matrix A that you see in the one-shot problem, then you could hope that the bulk is going to break here into something that does not overspill on these two eigenvalues that don't move much. And then you can still use the second eigenvalue to detect the communities. But we know that this is not true in the sparse regime. A doesn't work. However, if you use B, which is a non-backtracking operator, then this will be true. The picture is in 2D because it's complex valued, but essentially you do have that the second largest eigenvalue corresponds to an eigenvector that is close to the one that locates the two communities. Okay, so without the adversary, before we do the adversary case, we know that both the method of moments and the non-backtracking operator get you the optimal threshold for this problem, so it's a problem that is solvable. Okay, now I'm just going to add something to make the problem more interesting, is we add an adversary. And the adversary can do the following. You can take your graph before I draw from either class 1 class 2. The adversary comes, it can modify order log n edges in the graph, and then it shows this modification to you, and then you have to decide where the graph comes from. So what happens here is that if you do this adversary, both the method of moments and the method of non-backtracking break. And they break because the adversary can put a click inside one of the group, for example. So it can even be a mountain adversary that only add edges inside the cluster. And then you will create the second eigenvalue will now be dominated by an eigenvector that is localized on this click. Okay, and this is true for the non-backtracking method. And what happens for the moments is just that the counts become completely disrupted by this click. Okay, so now we know that there is a way to get around this. It's the powering method. It's you take your graph and you add an edge between every vertex at distance r. So you complete the graph. So the operator of graph powering is this matrix. Is 1 I plus I. The r is greater than 1. So you just complete the graph by connecting every vertex at distance at least r in the graph, at most r. This is going to get you the optimal threshold, and it's also going to be robust to this adversary. So again, the problem with an adversary is not something which is impossible. So we know at least one algorithm, and there's another one. So we did it with graph powering in here. There's another one which is very related that has been done also here. So it is possible to test between the two models with the adversary. What's interesting is if you try to use now GD, and what you do is that you sample from, you get many samples from class 1, polynomial number of samples for class 1, same from class 2, and we train GD in polytime. Then we believe that it's optimum without the adversary. So that means, I don't think it's proof, but we believe it will go down to the optimal threshold. However, there is one adversary, and that's my last phrase, that is going to break GD. And it's not the same time of abstraction as here. Here, what the adversary would do is it will take all the cycles of length k, which is less than log n, and it will break those cycles. And if you do that, if you break all these short cycles, then we believe that you can still succeed with power spectral, that has been proved. But we believe that GD will no longer be able to classify with string Bernheim. And the technique, we can show you some special case, and we would like to show you some arbitrary IID initialization, but we can show you some non-special case, but we believe this to be true for any IID initialization of neural nets. Okay, so that's the
So Emmanuel, there's a question from Joe Neiman who's asking, can you comment on what happens if you allow more than log n changes, or how this changes as a number of edges?
yes. So for let's see if I can remove those. Need to remove this. Okay, good. So in here, what you can tolerate for the number of edges for the adversary is essentially n to the epsilon for epsilon small enough. So you can tolerate quite a bit more than the log n that I mentioned. So I just took log n as an adversary budget that was below what you can tolerate for this type of method, graph plotting and graph distance. Here, I think that as long as you give it any k which is growing, as long as you manage to break down all the cycles of length k for any growing rates, then you would actually have GD that is in trouble on a random ID initialization. Does it answer the question? I don't see the chat, but maybe I have to stop sharing.
This was in the Q&A. Yes, Joe says that. Yes, thank you.
Okay. Great, thanks.
So I guess if there's no other questions, or we can continue in the Gather Town later. But yeah, thanks very much, Emmanuel, for the talk.
Okay. Thank you.